Two comments before I move on to the second part. Based on Carl's comments, the two maps I showed about the solar magnetic field for solar minimum, solar maximum, these were not magnetograms, which is the measurements of the magnetic field. This was a potential field extrapolation to several solar radii above the surface. So that's one comment. The other comment is that even though we reduce the galactic cosmic rays intensity for accretion disks, we can have another component of energetic particles that come from the star, what we know as solar energetic particles in the solar system, and these particles can actually ionize more. So it's a balancing thing. So the second part is even more speculative than the first part, because the first part, we can measure rotations of stars, we can measure activity level, we can have some observations of the magnetic fields. The second part will deal with stellar CMEs, and this is something that we essentially cannot measure at this point. So we're going to try to think together maybe how coronal mass ejection change in time and in stellar evolution, or change in time. We can start with the 1960s, where CMEs were free and happy, and they had this Volkswagen van. Then in the 1980s, they got this puffy haircut, and they changed the Volkswagen. And of course, today they work on Wall Street, and they have a Lexus. So that's CMEs in time. Now, seriously speaking, again, we're talking about CMEs and stellar evolution. So here are the questions we would like to ask. How do CMEs change with stellar evolution and the change in stellar activity? And we can divide these into two aspects. One is how the changes in the star affect the initiation of CMEs. And then how the change in the star changes the background at which the CME are propagating through. So how it affects the propagation of evolutions of CMEs with the changes in the stellar or the astrospheres themselves. Now, observations. We have stellar flares, and we have solar flares that we can associate with CMEs, but that's all we have. So the goal of everything we're going to do is to essentially make assumptions, think about what may happen, and extrapolate relations that we know from the sun to other stars. And this was mentioned already in previous talks. So the impact on CME initiation. The first thing that we can consider is that if we, as I mentioned in the last part, the concentration of magnetic activity is located at higher latitudes for young active stars, we know from the sun that CMEs essentially come from the region of active regions, where the activity is concentrated in. In the case of the sun, it's about 30 degrees from the equator or lower. But if we have this high latitude activity, and we assume that the CMEs are launched from that part, the CMEs will essentially go in polar trajectory, and they won't really exist near the equator, where, for example, we have planets. So this is one thing we can think about it. Where are the CMEs launching in these young active stars? The other thing with respect to the initiation is the scaling of the magnetic fields with time. We know that young stars are more active probably because they have a much faster rotation. So they have this excess of energy to boost the magnetic field overall. So we can think about these red lines as the overall stellar field. And you can think that the CMEs themselves, there are two options. Or one option is that they're not really scaled with this overall increase, and they're still coming from small-scale active regions, like you see here. Or they can be scaled accordingly, and they can be larger, they can be more energetic, and they can carry more magnetic flux. And there's the consequences for these two scenarios may be very different. For example, if the CMEs remain small and the overall field is boosted up, then the CMEs become less important in the context of the building up of the astrospheric magnetic flux, because in the case of the sun, during solar maximum, the heliospheric magnetic field magnitude goes up. And we think it happens because CME is essentially adding more flux to the heliosphere. And then as we're approaching solar minimums, the number of CME is reduced, so the flux get back to its kind of what we call the floor value. And during the recent extended solar minimum, we had an opportunity to really estimate this floor value because there are essentially no CMEs at some point. So CMEs can play a role in adding magnetic flux into the astrospheres. And if they're very small and weak, then they'll matter less. But if they're scaled just like the overall increase, then we can still assume this relation between the overall flux and CME flux and investigate the evolution of the overall magnitude of the magnetic field in the heliosphere or the astrosphere.
How about CME speed?
The question is, what about CME speeds? We don't know. So if you assume that the CMEs are scaled with the overall size and activity level, then they'll have more magnetic flux. They probably will be more energetic. Now, the speed is a function of the initiation mechanism of the CME, not necessarily the kind of initial energy you have available in the magnetic field. Now, we'll show this in the next couple of slides. So it's more of about how much energy you actually store in the CME before you erupt it than the size, for example, of the CME or the initial flux rule. Yes. Well, the flare, that's because the CME speed is the kinetic energy of the CME, and the flare is the radiation energy. And they're tied to each other, and I will talk about it later. But so you can definitely relate the flare and the speed for the sun, for solar CMEs, but to relate the size of the original CME to the speed is not necessarily linear, because the function of how much energy you actually store via the initiation mechanism, and wait, just 2 more slides and I'll discuss it. So the scaling of CMEs with the overall increase in magnetic field is an open question. There it is. So how do we think CMEs are initiated? You can imagine a flux rope. It's a flux tube of magnetic field that is attached to the surface of the sun. This is a simulation of Yuan Fang and Sarah Gibson from 2007. They're actually here at AGO. And we start, because we have motions on the surface that these two field lines, these two edges of the field line attach to each other, you start to build up a twist in the magnetic field. You can imagine a slinky that you start to twist in 2 opposite directions with the two edges. So you build a tension, the same with rubber band. You build a tension in the magnetic field, and then probably the magical word of magnetic reconnection essentially cut this flux rope and release. We have a sudden release of this energy.
Actually,
Yeah, we need something to trigger the sudden eruption. But the point is that we had a slow storage of energy before we triggered the CME. And the higher the energy we store, the larger or the stronger will be the CME will be. Now, for fast rotating stars, again, we have this azimuthal tangling of the field in the corona. So we can imagine that flares, and now a CME will generate flare by a mechanism that Rachel showed yesterday. Essentially, we have particle acceleration at the top that falling back to the star, to the surface, and they heat it and emit X-rays and UV emissions. You can imagine different type of CME or eruption that is generated due to the strong azimuthal tangling of the magnetic field. So instead of storing the tension in the magnetic field via the tangling or the twisting, we actually have this stretching of the magnetic field in the azimuthal direction. And this is a map I did from a simulation I did of FK Comet. It's a F-giant star. Don't get me guaranteed for that. I'm not an astronomer. It has also a fast rotation of about 2 days. And you can see this tangling of the magnetic field. This map shows the equatorial plane, and these are the regions where the tension, the magnetic tension is high. You can see it's clearly along this highly stretched loops in the azimuthal direction. And then we can store energy this way, and then again have some kind of triggering mechanism like reconnection or instabilities that will release another CME and a flare. But this is different mechanism than the traditional CME that we have on the sun. And also, these flares may be, I mean, the scale of these loops is the scale of the Helmut streamers. These are the largest loops we have in a star. So we can store a lot of energy, and we can probably explain the very large flares with such a mechanism, just because of the scale of the loop. Yeah? Yes, this is a model. The magnetic tension here is defined by the B dot grad B term in the Lorentz force. This is, in principle, this is, the question was about the inclination of the CME. We cannot really, I mean, when we see a stellar flare, we don't know where it comes from, what its inclination. We have no idea. Yeah, it's probably going to be centered near the equator, but again, you can have asymmetries in the magnetic field that will move it up or down. And of course, you have an overlying field on top of that. So the eruption needs to go through an existing field, which is not necessarily symmetric. Now let's talk about the propagation of CMEs and evolution of CMEs and its dependence on the structure of the existing field. And again, as we talked about, the astrospheric field is affected by the rotation and the magnetic field strengths, etc. So if we look at these young active stars, this is again AB Dor. This is a three-dimensional map of the magnetic field structure in the corona. This is the ZDI map of AB Dor that I obtained from Gati Hussein. And this is the three-dimensional structure. And again, we have this highly tangled magnetic field in the corona. So what will that do to the CMEs? Keep in mind that these tangled loops, first they have more mass there. So the CME has to go through more mass. The azimuthal field component drops slower than the radial component. So the magnetic field along these field lines is stronger than a particular magnetic field strength if we would consider a radial field line. So the CME has to go through a stronger magnetic field and just more mass on the way. And I did a toy modeling of CME on AB Dor. This is the equatorial plane. For a solar radial field, it would just go zoom out. But here you can see it's kind of making its way. Not sure where we're going. Eventually it goes out, but it takes a longer time. And you can see there's a slowdown of the CME as it goes up instead of the opposite. CMEs usually are accelerated in the low corona, but here it's actually slowed down. So the possible consequences are slowdown CMEs. Will this behavior generate more shocks or less shocks in the heliosphere or the astrosphere? We don't know. And will this kind of CMEs will have positive or negative consequences on the transport of galactic cosmic rays? What will this kind of CMEs will do to the overall structure of the astrosphere, and what will be the impact on the transport of particles in the astrosphere? We don't know. Now let's talk about the role of CMEs in stellar spindown and stellar evolution. And this was again discussed mentioned by Brian and Rachel. Here I'll discuss it in a little bit more details. Again, this is the relation between age and rotation, which clearly shows the Skumanich laws. It clearly shows a spin down of solar analogs with time. When they're formed, they're very fast. The rotation is very fast, and then it slows down to solar rotations or even less than that. Now we need to explain why it happens, and the most common explanation is, again, the concept of magnetic braking. It's the spin down of the star by a magnetized wind. It was introduced by Weber and Davis in 1967. I think they were working in Boulder as well. Does somebody know? Let's see you. You should know. Okay. That's fine. Here's the story. This is the star. This is the Alphen point. This is the collection of points where the wind speed exceeds the local Alphen speed. So all the field lines above this red circle are open up to the heliosphere or the astrosphere. Now, within this region between the surface and this Alphen surface, we call it the Alphen surface, excuse me, we have a conservation of angular momentum, but once the mass or the plasma reaches these open field lines, they're carried out by the stellar wind to the edge of the stellar system. And again, because they're following the field lines, the field line is so long that it applies torque on the star and spins it down. Now, this mechanism works only if we're talking about long time. So we're talking about billions of years, that the lifetime of the star. It's not a short-term effect, it's a very long-term effect. And Weber and Davis came up with this formula to estimate the spin-down rate of a star, and you can see it depends on the rotation rate. This is the average distance of this Alphen point, RA, and this is the mass loss rate of the star. And as Brian already mentioned, this is one of the reasons we care about M dots from other stars, because it's important for, it's very important to define M dots in order to define the spin-down rate of stars. It's a very important ingredient for any stellar evolution model we have. So we need to know M dot. But we cannot measure M dot. We can indirectly measure it, again, using this hydrogen line measurements. But there are no direct measurements of M dot of cool stars or solar analogs. In that context, it's nice to mention the faint-Young paradox. How many of you have heard about this? Okay, few. That's good. Here it is. The young sun luminosity was about 30% less than the current days. So if you just calculate the luminosity of the sun all the way to the Earth, and you calculate the incoming solar flux, you get, and you calculate based on that the surface temperature on the Earth, it was below freezing. But we have geological evidences that for liquid water on the surface of the Earth. So we have a paradox. We need to explain what was the additional heating mechanism that occurred in the Earth to have liquid water on the surface, where the surface temperature was above freezing. Yes?
How long ago?
I think we're talking about 1 billion years old, maybe 700 million. Yeah, it's the 3.8 billion years ago is roughly. And here is this is the famous Sagan and Mullen paper from 1972, where they introduced this paradox in the context of the atmosphere of Venus. And this paradox essentially started greenhouse gases heating in the atmosphere, and essentially what we call global warming nowadays. Because the greenhouse gas, well, I'll just move to the next slide. The solutions are greenhouse gases. So we can have gases in the atmosphere that lock the heat and increase the temperature. This is one way to solve this. As I mentioned before, there's some people who suggested that the reduction of galactic cosmic rays for the young sun led to an overall increase in the temperature on the Earth, and that can explain that. In our context, or in the context of solar mass loss rate, if the sun was more massive by about 10% at the time, we do have no problem, because the luminosity is high enough, the temperature is high enough. So one way to solve this problem is to show or to demonstrate how come we have a more massive young sun. Mass loss rates of cool stars, as shown before, ranges between 10 to the minus 15 to 10 to the minus 12 solar mass per year. And this is a pretty good, I think, range that we can know that this is the range we have. The solar mass loss rate, if we just take typical solar wind parameters at 1 AU, density of about 5 cubic centimeters, 10, solar wind speed 450 to 600, and we just multiply it by 4 pi 1 AU squared. We get a value of 2 to 3, 10 to the minus 14 solar mass per year. Brian showed a paper of mine from 2012. 11, I actually looked at many solar wind points, data measurements all over the heliosphere, and this is what we get. So this is a very good estimation overall. Now, the question is, what can we have from CMEs? Because CMEs, they take mass from the star, right? So what's the rate of CME mass loss rate of the sun? So we can get a rough estimation for that. Typical CMEs carry between 10 to the 13 to 10 to the 17 grams. Over the solar cycle, we have about half a CME per day during solar minimum to 4 or 5 CMEs per day during solar maximum. So we can assume an average of 2 to 3. And if we just multiply the CME rate by the CME mass, and we divide by the number of seconds per day, we get a number of about 10 to the 10 grams per second. And this translates to about 5, 10 to the minus 16 solar mass per year, which is almost 2 orders of magnitude less than the ambient solar wind mass loss rate. So on the sun, CME, a mass loss rate to CME it's not really important. But, so that's what we have. But what if the CME rate increases significantly for very young active stars? Can we get to the point that CME mass loss rate becomes significant? So we can do this estimation in a rather simple way. And the other question that we need to ask, and I mentioned it before, how to scale CMEs to other stars. And for that, we can use, again, these relations that were developed for between solar flares and solar CMEs. Gopasmali and Yashiro, and also Alisa Aarnio. In the recent years, they look at GOES data for the X-ray flares. This 0 to 8 angstrom instrument that looks at the X-ray, and they took the CME mass from the LASCO instrument on board SOHO, which measures the white light or Thomson scattering from a white light in the corona. This is a measurement of the mass, essentially. So they compared the mass of CMEs and their flare energy of CMEs, and they got this relation between the mass of a CME and the flare energy. Because the flare is what we can actually measure on other stars. And that's the relation we would like to get. Jeremy Drake et al. Did similar thing. They essentially were based on the same relations that I showed before. And they assume that the mass, again, is some parallel of the flare energy. And again, this is the GOES flare energy. It's important to mention it's not the total flare energy, or you can define the flare energy in different ways. This is the GOES flare energy. And again, they got this relation with these coefficients. And here we just show the different, and you can also do the same with the kinetic energy of the CME and describe it also as a power law of the flare energy. And these plots show the distribution or the scattering of these two, where these two lines are the power laws that I show here. These power laws, what they show is very important. They show that the bulk energy of the CME is in the kinetic energy. The fraction of the flare energy in the CME is not more than 10%, or even much less than that. Yes, Rachel. Yes, I mentioned again and again, it's the GOES flare energy. But still, the fraction of the flare energy is significantly lower than the actual kinetic energy of the CME. That's where most of the energy is, just a second ago. And that's why we can't really see it in other stars, because we cannot really see the CME itself. Yeah. Okay. Okay, fair enough. But it doesn't matter because here we have both. So we can have a power law of the mass of the CME as a function of the flare. You can treat this E as the stuff we can actually measure. So we can get some expression for the mass the kinetic energy. And from that, we can also scale, get a scaling law, again, based on solar CMEs, to relate the CME rate to the flare energy, E. So we have that. And from that, we can get the total power in the CME, which is just the integral of the particular flare energy over all flares. So now we can replace this dN with dN dE times dE, and just plug in the scaling laws we had, and we get this expression here. Now we need to find the coefficient K. If we assume that, and this is a questionable assumption, but if we assume that the total power should equals to the total power in X-ray of the star, then we can define K as the total power or total X-ray luminosity Lx times all the rest of it. And this is an assumption that it's tricky, because it depends on what band you're looking at, whether you resolve all the X-ray emission or not. Now, in addition, Gopalswamy and Yashiro, they also defined their association fraction of the flare energy, and they call it F. And this is a function that states what is the probability of a flare that we see to actually have a CME associated with it. And overall, so they also define this as a scaling law, but overall it says that if the energy of the flare is more than 10 to the 29 ergs, there's guaranteed a CME with that. So that's that the value of F is 1. And then they have a scaling of the lower energies with this power law. So as we go to lower energies, we see only flare, but it's less likely to have a CME associated with it. So we need to take into account this probability in the overestimation of the mass loss rates that CME carried out, because not all flares that we see actually have CME that goes away and takes mass. So with that function, we can estimate m dot due to CMEs, and it's the mass of the CME, which we know with the scaling law, times the probability that there is actually a CME there, times the rate of the CMEs, and we integrate it over all the energies we have in the X-ray, or in the flare energies. And we get this expression. It's long, but we know what all these coefficients are. So we can essentially now estimate m dot to CME. Oops, yeah. And the values are really high. For young, very active stars, you can see that the result is 10 to the minus 11 to 10 to the minus 10 solar mass per year. And this is already 1 to 10% of the total volumetric luminosity. So that's a lot. Aarnio et al. Got even higher values of 10 to the minus 9. So these are very high mass loss rates. And it's worth to mention that most likely these scaling law break down at some point, and they don't hold because of the fact that they reach energy that is comparable with the total volumetric luminosity of the star. Here we're not talking about single CMEs that can be really energetic, but this is kind of a long-term integral over the CMEs. So we cannot get such a high level of energy only from CMEs. We don't have we don't have a place to bring this energy from. Drake et al. Mentioned that most likely the upper limit is around this number, slightly higher than the large values of the ambient stellar winds that we think these stars have. Aarnio et al. Also estimated the torque on the star based on CMEs. So in the original form, this m dot would be the m dot of the stellar wind. They simply replace it with CMEs and got some estimates on that. My personal opinion about this work is that it's probably not realistic, again, because the values are so high. Now, with respect to the faint-Young paradox, this is an interesting result, because you can think about CMEs in current days. They come from lower latitudes, and they interact with they can't, if they go near the equator, this is where the maximum torque is applied on the star. So this way you can take mass loss, take mass from the star via CMEs and also apply some torque. But if we assume that in active stars, CMEs appear at high latitudes where the activity appears too, so, whoops, oh, I went backwards, okay. If the CMEs are launched at higher latitude, they can take all this mass away, but they don't take a lot of angular momentum because as we get closer to higher latitudes, the torque decreases and goes to 0 at the pole because there's a latitudinal dependence on the torque. So if we can take a lot of mass at high latitudes, this is a way to take a lot of mass from the sun or from the star without losing angular momentum and maintain its activity level, which is high, for a long time. So with this, we can explain how come the young sun was more massive and was more massive and lost a lot of mass without losing angular momentum for a long time. And it can explain the paradox in principle. I was in a meeting a few years ago about the faint young sun that met geologists, atmospheric scientists, and astrophysicists. And there was a lot of discussion about whether there is a paradox at all. There was a lot of debate about the actual evidence that raised this paradox. So it's still an ongoing work. Okay, so the last part, the last thing I would like to mention is the effect of CMEs on closing planets. And this is a work I've been doing for some time now. And it's exoplanets, of course, everybody excited about this, and you know, there's a lot of interest in that. As you all know, we found many exoplanets. The first exoplanets around Sol's main sequence star was discovered in 1995. It was a hot Jupiter, which are gas giants that are located very close to the planet, to the star. Since then, we found many of them, especially after the launch of the Kepler mission. Now we found hundreds of them. And indeed, we still see many planets that reside extremely close to their host star, less than 0.1 AU from the star. And some of them reside essentially inside the corona. So the question is, what is the space environment around these planets, and what are the consequences of the close distance? And CMEs as well. It's important because these stars need a magnetic field or some other mechanism to protect their atmosphere, because the intensity of the stellar wind at these distances is very high, mostly because the density is much higher, about 3 orders of magnitude higher than 1 AU. And this can apply a stripping force, and the atmospheres of these planets can be lost. And we think that part of what happened to Mars in the past. Part of the Martian atmospheric loss occurred because of the solar wind. Now, with respect to CMEs, there was a very little work done on this subject. So one of the only papers that were done by Khodachenko, I think, in 2007, they scaled the CME mass to the close distances of the planets. They took solar CMEs, and they took the typical mass of a typical CME at Earth, and they just scaled the density down or up to get the density at closer distances of these Ds. And these are the values of they look at range of mass of densities between N min and N max. And they simply took the famous expression to calculate the pressure balance between the magnetic field of a planet to the stellar wind. So the stellar wind dynamic pressure is the density times the mass times the stellar wind square. In this case, it's the CME speed. And the CME speed they took was 500 kilometers per second. It's typical for the sun, even though the strong CMEs are over 1,000, so it's at least a factor of 2. And this is the expression for the distance of the magnetopause. This is the place where the magnetic field of the planet balances the dynamic pressure of the stellar wind. And this M is the magnetic moment of the planet, and this is the dynamic pressure of the wind, or the CME in this case. And they calculate this distance for a different range of parameters for the CMEs and the planets. And this is the distance from this, of the planet from the star. And this is the mass of the star, of the planet. No, this is the stellar mass, you're right. And this is the habitable zone if we only consider the luminosity of the star and the distance. So you have the luminosity coming all the way to the top of the atmosphere of the star. We can calculate what is the right temperature. And we can define a range of distances where we can have a not too hot and not too cold temperature. We call it the habitable zone. So this is this shade here is the habitable zone. However, they show that essentially all this region, the magnetopoles of the planet, assuming a given magnetic field, is very compressed, and it reaches almost all the way to the top of the atmosphere. So there's a poor protection of the atmospheres of these planets, even though they reside in the habitable zone, according only to the radiation. So this is one way to demonstrate why the space environment matters for habitability. I did a simulation of a CME heating and a closing planet. You can see here, this is the star. The CME is represented by this white shade, and the magnetosphere of the planet is represented by this blue shade. These are magnetic fields of the star and the planet. And you can see that the CME essentially blows off most of the magnetosphere. This planet resides at about 10 stellar radii. So imagine a planet that sits 10 solar radii from the sun and is hit by a CME. And here I show on the right, this is a prediction of the aurora on this planet. And you can see it's all over the place. It's not confined to high latitudes like in the Earth case. So the stripping of the magnetosphere is very significant here. And another thing I looked at is the atmospheric protection. So I calculated the mass flux on spheres around the planet in 3 different distances. 1.5 planetary radii above the surface. And essentially a negative value represents an influx of the CME to the planet. Well, if we don't have negative values, it means that there's a good protection. The CME doesn't penetrate all the way to the sphere. And you can see that for a half a Gauss field, which is roughly the Earth field is 0.3 Gauss, there is a strong penetration at 2 planetary radii, but there's almost no penetration at 1 planetary radii above the surface. So this is about 6,500 kilometers above the surface. If the planetary field is stronger, 1 Gauss, which is roughly Jupiter's field, Jupiter's 4, you can see that even at 2, the penetration is very weak. You can see here it goes all the way to 60, but here it's 2. So it's significantly reduced by the increase of the magnetic field. So magnetic fields of planets are very important for the discussion of the habitability, because without magnetic fields, most likely these planets won't sustain their atmosphere. And they must have a magnetic field to sustain the atmosphere. And it's important to determine what are the magnetic fields of exoplanets in general. Another difference that I would like to stress in this kind of closing planet and CMEs, there are 2 things. These planets, their orbital motion is very fast. Their orbital period is sometimes 2 or 3 days, something of the order of 150 kilometers per second orbital speed. And you can see that before the CME hits the planet, the magnetosphere structure is azimuthal, almost azimuthal, as if it's like a comet tail. And that's the result of the fast orbital motion. But as the CME hits the planet, you can see that there is a transition of the whole structure of the magnetosphere by almost 90 degrees. And the transition between here and here occurred in the simulation within about half an hour. It's very fast. And what happens to a magnetic field when you change it? What's the BDT make? Electric fields and currents. So only this change can drive a lot of energy and currents into the ionosphere of these planets. So it's something to continue to study. The other thing I would like to stress is that look at the size of the CME and the planet. They're comparable in size, right? This is a CME at the Earth. The Earth's magnetosphere, not the Earth's magnetosphere is this dark point. So the CME doesn't care about it. It's just move. But here, because the two bodies are similar in size, the CME is highly affected by this interaction, unlike the Earth's case. So this is another thing to keep in mind, that for closing planets, the CME hasn't evolved enough and grow in size that it can be highly affected by the planets, and this may have consequences for the whole structure of the heliosphere. Because, as I mentioned before, CMEs add flux into the astrospheres over time, and if we break them apart during the very early stages of the CMEs, it can have consequences with that respect. And here I just show you the equatorial plane and the simulation of the CME. This is after 20 minutes, 1 hour, 1 hour and 20 minutes, and 3 hours. You can see this is the initial CME as it's approaching the planet. You can see again this comet-like tail of the planet. And you can see that the CME breaks by this interaction. So this is another thing that I would like to highlight in this context. So there's a lot of work to do on exoplanets and space physics, essentially, in the context of what is the space environment of exoplanets and what's their role in planet habitability, which is the main driver for this whole field of exoplanets. And I think I'm done. Yeah, okay, so I'll just wrap up things. This is essentially things that we can get improvements with like in the near future. So we have to keep in mind, again, astrophysics is very limited in data comparing to heliophysics. We know much less than what we know in space physics. As I mentioned before, we have a growing amount of Zimmer-Doppler imaging maps that give us information, at least on the large-scale distribution of magnetic fields of other stars. And we can use these maps to drive our models and study these systems in detail. Stellar winds from cool stars, we need more observations so we can have better constraints what stellar winds of solar analogs actually are. And stellar CMEs, this is an ongoing research subject. We need more flare data. And there are very recent attempts to, again, as Jeff mentioned, to observe radio signals from CMEs in other stars, in type 2 radio bursts, etc. And we need to determine what are the magnetic fields of exoplanets, or what they likely are based on where they are and where they're formed, because that's an important ingredient in habitability. And the last thing I would like you to keep in mind is that the only proxy for stars we have, real proxy, is the sun. So the sun is a star, and we need to treat the sun as a star for some things. But it's even more important to look at other stars as if they're the sun, because we have a lot of, I'm not talking about data. We have a lot of information about the sun that is not applied to other stars. People don't view other stars as the sun, including all this information we already have from the, the sun, the heliosphere, the solar wind. It's all important components of stellar physics. And we need to keep in mind that the sun, we know a lot about the sun. So just take that and implement that in astrophysics. And I think that's it. Yep. The space environment, the interplanetary environment, if you like. Yeah, this is the medium where, so people consider planet formation based on the disk environment. But from then, once the planet's formed, they don't take into account the environment anymore, usually. But it's still there, and it has an impact. So I think people should account for that more in in astrophysics research. Yeah. Yeah, of course. So the question was with respect to the open versus closed magnetic flux in stars in the context of the mass loss rate. The stellar activity indicators that we have come from the closed flux, from the closed loops that get hot and emit X-rays and UV, etc. The mass loss rate or the mass loss occurs along open field lines. Now, in the sun, what we know is that over the cycle, the open flux almost doesn't change much, while the closed flux changes by an order of magnitude, or even more. And that's very consistent with the continuous or the pretty continuous value we see of the mass loss in the solar wind measurements. So the point is that first maybe it's the indicators that we have for activity are not very good indicators for the mass loss because maybe they're not related to each other. The other point is that based on the solar observation that the mass loss and the open flux are rather constant over the solar cycle, maybe that suggests that these two parameters may be fundamental parameters of a star. And then the question is to what other parameters that you can measure you can relate them, like stellar potential well, gravitational well, the ambient weak magnetic field that you see all over the quiet sun, like the salt and pepper kind of small scale field. You can probably relate these two parameters to these observed or measured parameters and treat them as if they're like fundamental properties of the star. So the CME as it propagates into the heliosphere, it goes through what we believe and we call the interchange reconnection. So at some point it will get to a kind of a balance between the open flux. It will be open as well, but it will add magnetic flux into the heliospheric flux. So that's how you increase the heliospheric flux during solar maximum. You push more CMEs with new flux that is emerging from the surface into the heliosphere. You open them up and you increase the overall flux. So eventually this mass is kind of assimilated in the heliosphere. Does anyone have an idea?
No, I gave you the answer. I gave you the answer yesterday. Okay. I want the answer.
I can rephrase the question. I can rephrase the question. We said that giant stars are not solar analogs. They have different wings, different corona. Why we care about this giant? And that's the reason. Wow. Kind of. Yeah.